Hello and welcome to Sigma Phi's Distinguished Lectureship Series. I'm Katie Burke. I'm Digital Features Editor at American Scientist. I'm here today with Lance Bosart, who is a meteorologist at the University of Albany. Lance, thanks for joining us.
Thank you.
Before we start, I'd like viewers watching us live to note that you can submit questions to this discussion through the chat window on the Adobe Connect site, or you can submit them through Twitter using the hashtag AmSciTalks. That's AmSciTalks. And also, we'll be live tweeting this interview. So you can find the live tweets at that hashtag, AmSciTalks. Sigma Psi members can also discuss this topic afterward by logging into the Sigma Psi Communities page. So, Lance, you've been studying an array of weather and atmospheric processes since the 1960s. What was it about weather that captivated you initially? Were there any weather events that you remember fascinating you as a kid?
Yeah, that's how I got interested. I think it was Hurricane Hazel in 1954, which produced the strongest wind gusts to this day ever measured in New York City. And I was just between 11 and 12. And it was, I've never seen it so windy as in Hazel, but it didn't rain much. And I was frustrated. I said, why isn't it raining? Hurricanes are supposed to have rain, a lot of rain. So I asked my father, why isn't it raining more? We're having a hurricane. He said, I don't know. Go ask your mother. So I asked my mom the same question, and she said, go ask your father. So that frustrated a little kid in that area. It was only much later that I figured out why that was when you started studying the field of meteorology, that the rain's on the left side of the track and the wind's on the right side of the track when you have a
Uh-huh.
storm at higher latitudes, like making landfall.
Mhm. And what was it like during that hurricane? What do you remember seeing?
Uh, Trees bent over all the way to the ground in some cases, very, very strong winds and hardly any rain.
Hmm. Yeah.
But back when I was growing up, we had Hurricane Week every August or September. There was always a week when there were hurricanes threatening the East Coast and heavy rain, and that just
Uh-huh.
seemed like the normal state of affairs. But didn't know then that hurricanes come in cycles, and some there are decades when you have lots of storms, and other decades when hardly anything happens. Like we're in a very quiet period since 2006.
Uh-huh.
Sandy aside, there's really been a remarkable lack of hurricane activity on the Gulf and East Coast in the last 10 years.
Uh-huh. And so, how has our understanding of hurricanes changed over the course of your career over 50 years?
Oh gosh, partly
I
because of
know it's a huge
advances
question.
eh, well, partly because of advances in instrumentation. The
Yeah.
satellites coverage didn't really start until the 1970s, but quantitative measurements from satellites didn't really begin until the early 80s.
Hmm.
And resolution increased where you could get information on the environment of a hurricane. And then we have the NOAA research flights on the hurricanes, on the P3s that fly out of Florida,
Hmm.
that take measurements whenever there's a storm threat. But they're always out there on research missions as well, collecting data, have Doppler radar on board the aircraft to
Have
get
you
a
ever
lot of
been on one?
measurements. Yes, I
What
flew
is it
into the
like?
eye of Hurricane Gloria in 1985.
Wow.
I've been on rougher, useless air flights.
Hmm.
Uh, so yeah, so the last maybe one minute going into the eye, it's a little bit bumpy to say the least. My wife wouldn't like it, but
Some
you
slight
know,
turbulence there.
some slight turbulence. Yeah, but I mean the plane is doing what it was designed to do. If it's
Hmm.
windy and it's bumpy, it's going to fly right through that and act like it's in the air. So,
Hmm.
but then you have grapple and you have this huge noise on the outside of the airplane from all the grapple, all the ice particles in the eye wall of the hurricane.
Interesting.
I didn't
Grapple is
fully
the ice
appreciate
particles on the outside.
in the eye wall of the storm,
Huh.
and it's part of the microphysics process of hurricane of how it forms. But I didn't fully appreciate the importance of ice microphysics until I flew into the eye wall of Hurricane Gloria and recognized how much ice there was in a tropical storm. I mean, I've read about it, but until you experience it, you don't really,
Right.
really see it that way.
Yeah. And so that's just one of the many ways that instrumentation has changed over the last 50 years.
Yeah,
Uh,
the numerical forecasts have gotten the models. We had
yes.
no clue how to make a prediction of a future, whether a storm was going to intensify into a hurricane, which
Mhm.
direction it was going to move, when it was going to recurve into higher latitudes. We couldn't even think about doing that 25, 30 years ago. But now
Mhm.
we do that routinely. There are still a lot of issues, but on the lifetime of my career, the progress in forecasting tropical storms has just been remarkable
Yes.
improvement.
And there are a couple of storms that have really stood out in your career. One was early in your career, and it was Hurricane Agnes in 1972. So tell us a little bit about that storm and why it stood out for you, and what made it interesting, and what you learned from it.
Well, Agnes was a storm that came in on the Florida Panhandle
Mhm.
and in 1972 in June and moved northward east of the Appalachians and re-intensified a bit over land and became what's called an extratropical cyclone. So what right there was the process of how a tropical cyclone becomes a mid-latitude cyclone. It's called extratropical transition. And nobody was researching that aspect of tropical cyclones at that time. In fact, my student Jeff D'Amago and I wrote some papers about that storm, and we had the whole field to ourselves. Nobody was even doing anything about that, which I found awfully hard to believe, given its importance. But the other thing that occurred was that there was some flooding well ahead of Agnes in the northwestern Pennsylvania and southwestern New York in the Chemung River Valley, and that rain was well ahead of Agnes. And so a couple of years later, Fred Carr was my first postdoc. He's now the current president of the American Meteorological Society, or he just stepped down last month after a year as president of the American Meteorological Society. We zeroed in on trying to understand why all that heavy rain occurred because Agnes, it was clearly related to Agnes, but Agnes was down in like Georgia at the time you had all that heavy rain in in New York and Pennsylvania, in Western New York and Western Pennsylvania. And so I said, how can this be? What's going on? So we wrote a paper about it as we diagnosed it, and we discovered that you can get these exceptionally heavy rains when the moisture from the tropical storm is exported thousands of kilometers away from the storm into the equator entrance region of an upper level jet stream. That's a very favorable environment for converging that moisture and making rain out of it. Um, and that became what was known as the predecessor rain event. Only then, when we wrote the paper back in 1978, I wasn't smart enough to call it predecessor rain event. That came much later in the
Uh-huh.
1980s. I mean, in the 2006, 2007, when we wrote
So the
finally about predecessor, gave the name. One of the students here said, "Why don't we call these things predecessor rain events or pre's for short?" And
and
so
so
that's
the
took off.
so the rain is already there, creating the conditions for a flood, and then when the hurricane comes, it dumps more
Yes.
rain, and that makes the flooding
So
happen.
yeah,
Yeah.
that's why it's such a hazardous thing for flood. So it's almost like you're crossing the street and you see this big truck down the road, and you say, "I have to get across the street before that big truck gets here," but you fail to notice the small car that's about to run you over in
Uh-huh.
the interim. So a predecessor rain event is like a predecessor to the main event, but you can get as much rain out of a predecessor rain event as you can get out of the tropical storm itself. And so
Yeah.
if you get both, you're going to have a flood problem.
Yeah. We have a question from Ken Walter in the audience. He says, it seems weather forecasting accuracy has improved significantly over the last 30 years. What are the main factors causing this?
Most of the credit's got to go to increased observations derived from satellites, increased understanding of the dynamical and thermodynamical processes that govern it, and the tremendous advance in the state of the art of numerical weather prediction from the global forecast models.
Mhm.
By far, that is the most critical process. A lot of people work very hard to get these global forecast models to work, and they require assimilating all the data. So the term data assimilation is used, and by that it's meant taking all the observations from everywhere around the globe, all different kinds of observations, the surface, um, from radiosonde launches, balloons, from aircraft, from satellite-derived measurements, putting them all together into something that the model can recognize as an initial condition, which it can start integrating forward. And so that's a very, very sophisticated process to run these global models. But without that, we would not be making these advances. But that said, there's still a long way to go, as anybody who's had a busted forecast knows.
And you kind of at some point you started tackling some of the weather events and patterns that are difficult to predict. You seemed undeterred. What was it about those weather events that inspired you or drew you to such a challenging area at the time?
Well, I like to forecast every day, either when we have our forecast contest during the academic year at school, or
Uh-huh.
just because you learn something when you forecast. And
Uh-huh.
out of forecast failures, and I've had probably close to Avogadro's number of them in my career by now, out of forecast failures come learning opportunities. And so, and to understand what is it about the atmosphere in this particular case that led to the forecast going off the rails. So that's how you advance the state of the science. So science informs the weather forecasting, but equally important, weather forecasting informs the science. And so we have a name for that. We call it research to operations, or R2O, in which the science informs the operations. And operations to research, or O2R, in which the operations inform the research. So it's important to pay attention to the forecasters who have to put their skills on the line every day, particularly in critical weather situations. But they can teach us a lot about what are areas where there are problems with the science and problems with the forecasting. So it's a two-way street.
And in a way, the failed forecast is not a failure but a learning opportunity.
That's right.
Yeah.
That's how to look at it. But my wife would
Yeah.
tell you that a failed forecast is, when she wants to do something and I give a bad forecast, that she'll tell you, which is the important point of view, is never make a forecast you don't have to make, especially to a spouse or a family member or a neighbor. They remember all the bad ones for decades.
Yeah. So another storm, I want to return to another storm that really stands out in your career, that you've described as a watershed moment, quote unquote, for your field, and that's the Superstorm of March 1993. What was that? What happened? And what have you learned from it?
Well, that storm changed the whole business model of how we do science. Um, Prior to that time, the way we analyzed the storm anywhere, various parts of the globe and various institutions around the world, you drew a box on a weather map around the storm, and you analyzed what happened inside this box. And you didn't pay too much attention to what happens on the edges of the box. Air is moving in and out of the box from the sides, but we didn't have the global data sets available at that time in order to look at the thing globally. And so when the superstorm occurred, I just did some preliminary analyses as it happened and afterward, and noted that the disturbance in the upper atmosphere that triggered the storm had circumnavigated the northern hemisphere. And my faculty mentor, Fred Sanders, similar to that time, had been looking at disturbances. He was tracking disturbances that were circumnavigating the globe for another purpose. So we were starting to think about whether what happens here, what happens in the North Pacific, for example, matters greatly for what's going to happen in the eastern US a few days to a week later. So we were starting to think about the connections more globally rather than weather in a box on a weather map. And so my preliminary scratchings and analysis suggested that the disturbance that triggered the superstorm actually passed across the northeastern United States almost 3 weeks beforehand, dropped about 6 inches of snow in Albany, circumnavigated the northern hemisphere, and was much more potent the second time around because it phased with a disturbance further to the south and produced the superstorm. So that was an astounding revelation that could happen. I hadn't really thought about that possibility before. So in the fall of 1993, I was due to teach my advanced graduate level class, Synoptic Laboratory and Synoptic Analysis, Synoptic Dynamic Meteorology class. There were two classes, one the theoretical side and one the laboratory side. And in the laboratory one, I said, let's throw away, I'm going to throw away the entire existing curriculum, trash it. What we're going to do instead is just analyze the superstorm of March 1993, from soup to nuts. Figure out what happened and why it happened. Because for the very first time, we had global gridded data sets that we could use to look at not just North America, but to look at the Pacific, to look at Asia, Europe, the North Atlantic. We got the data sets both from the European Center for Medium Range Forecast. I'm indebted to Adrian Simmons over there, who sent me a whole bunch of gridded data sets. I'm indebted to James Harrell from the University of Utah, who sent us a bunch of data sets from the National Meteorological Center in Washington, D.C. So we had these gridded data sets, which meant we could track the storm around and track the disturbances and really look at all the interactions that happened well in advance of the storm. So that just changed the business model, how we do science. Taught me we had to think globally.
It really broadened the temporal and the spatial scale.
Spatially and temporally, absolutely. And so that just basically was a transitory moment, because that storm was so remarkable. It remains to today the deepest cyclone, non-tropical, to ever hit the Gulf Coast. It was 976 hectopascals or millibars when it crossed the Gulf Coast. That was extraordinarily intense for a mid-latitude type cyclone and not a hurricane. And then it just got stronger as it came up the eastern coast. But what made it so strong was a very, very strong jet stream and two disturbances phase. You had a disturbance coming in across the southern part of the United States that had a lot of tropical moisture with it. And you had a disturbance coming in from Canada to the northern part of the United States that had huge temperature contrasts associated, what we call baroclinicity, associated with it. And a lot of cold air. So the combination of the northern disturbance with a lot of cold air and lots intense temperature gradients, and the southern disturbance with a lot of tropical moisture, when they merged, produced a spectacular storm.
And so what are some other, we've got a question from the audience from Fenella Saunders. She says, what surprising weather events have led to advances in forecast models? So that's kind of, we've already talked about a couple, Hurricane Agnes and the Superstorm of March 1993. What are some others?
The President's Day storm, the first President's Day storm of February 1979. That was just, whoops, almost, the screen was going to go dark here. Just remind me to wiggle the mouse periodically.
Okay.
The President's Day storm of February 19th, 1979 was a spectacular, and I mean spectacular, forecast failure at the National Meteorological Center in Washington, D.C. They didn't appreciate even 6 hours in advance of the heaviest snow that they were about to get whacked. It was an absolute, complete, total surprise. And so I happened to be on sabbatical in 1978, 1979. I spent the first half of my sabbatical at the National Center for Atmospheric Research in Boulder, and the second half I spent at MIT. And so I was free to drop everything, and I recognized when the President's Day storm occurred that this was just an incredibly spectacular forecast failure. And when it happens in Washington, just to mention, you don't even have to have snow in Washington. All you have to do is forecast snow and the city shuts down. So to get 15 or 16 inches of snow and shut down the city totally unprepared, was just a disaster. And then, of course, the usual congressional grandstanding took place, demanding investigations and all this kind of stuff. But so I did since I was on sabbatical, I did a very comprehensive meteorological analysis of what happened. And so did then current NWS director Louis Uzzolini at that time. So we looked at the storm from different perspectives, and we learned from each other in doing this. In fact, Louis was we just reenacted the Superstorm in my class back in November, on November 29th of last year. Louis took time out from his busy schedule, and he came to Albany, and we spent a good part of the afternoon talking with the students and reenacting the science and the forecasting issues and what we learned from the President's Day storm. I mean, the President's Day storm just caused a lot of people to say, that's it, never again. We need to start thinking about doing things differently. So these disastrous forecasts are learning opportunities, not only for the science, but they're learning opportunities for the operational forecasters and the operational forecast system that the existing business model needs to be changed if you want to make progress.
And what about some events that are more recent, like since 2000?
Well, Sandy in 2012 was an interesting learning experience in there because I had always joked and said, is it possible to get a snow cane to have a hurricane that would have snow with it? Well, Sandy showed us that could happen. On the backside, and Sandy in West Virginia, they had quite the on the upslope side with the westerly wind, they had quite the snowstorm associated with Sandy. But Sandy is a storm that, as it came northward, got bigger and bigger in aerial extent. And some research I did showed that each time Sandy interacted with a trough in the westerlies, it got stronger and bigger. Not as a hurricane per se, but the storm just expanded in area as it interacted with more environments that were governed by temperature contrast outside the tropics. And the challenge with Sandy was the big forecast. I mean, there was the big debate about the European Center model showed their ensemble system showed more westward track of the disturbance, and whereas the American model showed more of an eastward track, but also had things going to the west. But the European model, fairly or unfairly, got a lot more credit in the media for catching on sooner that Sandy was going to do that famous left hook towards the coast. So there's been a lot of discussion about that. But the effect of Sandy was the Sandy supplemental, out of which the NOAA got about $50 million to get more supercomputers for the National Centers for Environmental Prediction. So so I think to make a joke, but to make a point, an occasional forecast disaster, especially when it occurs in a well-populated area where there are a lot of politicians, can be a good thing in the long run, because maybe you can improve your resource situation. Especially if you remind them, we don't have all the answers.
Right. And so, since you were in New York for Hurricane Sandy, I imagine gearing up, watching what was going on, and knowing that the storm was on its way towards you. What were you doing at that time to?
Well, we here in Albany, we were watching the storm, and we were going to be on the north side of the storm, so we would just get some wind. But with a strong southeast wind, we knew we wouldn't get a lot of rain here because we were going to get downsloped off the Berkshire Mountains to the east of us. The southeasterly winds coming into the Hudson Valley downslope off the mountains would dry out the atmosphere. So we would get not very much rain, which turned out to be the case. I think we only had like 0.37. But it was clear that down along Long Island, New Jersey, they were going to get really whacked with the storm surge, and was going to be an issue. And the interesting thing is, sometimes we're prisoners of our definitions. Sandy technically was not a hurricane at landfall, but if you looked at it, it looked like a mid-latitude storm, except about 50 kilometers around the center of the storm, where it still looked like a tropical storm. So it was like a large mid-latitude storm at landfall, but inside it was a kernel of an old tropical system, and it had the winds to go along with it. And so, what was that? Well, the insurance companies said it didn't meet the definition of a hurricane. So the practical significance of the argument about what it was is still playing out in the courts of law, because the insurance companies were trying to wiggle out having to pay for home repairs and building repairs like that, because, well, wait a minute, this thing, we cover hurricanes, we don't cover mid-latitude cyclones. So it's only arguments that lawyers can love. But so these definitions are not as clean as you sometimes would like them to be in the distinction between a tropical cyclone, hurricane, say, and a mid-latitude storm. It's not like turning on a light switch on and off. No, suddenly it's only a hurricane is now a mid-latitude storm, like switching the light switch on and off. No,
Uh-huh.
no, no. The transition is much more gradual. So
Uh-huh.
sometimes we're prisoners of our own definitions here.
Hmm. Oh, we have another question from the audience. This is from Diane Timblin. She says, could you talk a bit about human attempts to create weather events? As I understand it, there's been a good bit of research over the years into things like how to prompt a rainfall to relieve drought, even how to weaponize the weather. But I don't think cloud seeding or any other approach has yet been proven effective. Is this kind of research continuing? And if so, what do you think of its prospects?
Well, research should go on any subject. If there are people who want to research a topic, they should research the topic. That's what natural curiosity is all about. But the questioner is absolutely correct. Nobody has yet demonstrated a hard cause and effect relationship between, say, cloud seeding and enhanced rainfall.
Hmm.
Um, if there was such a relationship, I don't want to be anywhere near the parties getting into a big argument about that. Because if you could imagine an argument, I mean, this is only an argument that lawyers could love. If you get into an area where, say, you can demonstrate you've enhanced rainfall in region A and at the expense of region B, well, there
Yeah.
might be a lot of people in region B who are going to get very upset about that.
Hmm.
So I don't want to go there
Yeah.
in there. But I think the science is unclear on that. And as far as I'm concerned, there are no definitive statements one way or the other. But that's
Mhm.
not to say that there are people who don't like um, won't go out and see clouds. The Russians, for example, for years have tried to break up hailstorms by shooting cannons uh, uh, with ice crystals to seed the clouds and try to get many smaller hailstones as opposed to a few big ones. But the
Fascinating.
effectiveness of that has never been demonstrated.
Uh-huh.
But it's a little bit like there's a little bit of a snake oil component to a lot of that, which is one of the reasons
Hmm.
why serious scientists tend to stay away from that kind of thing. But that
Yeah.
doesn't mean you shouldn't pay attention to what's going on. But if you want to convince somebody there's what's going on, you have to get the hard evidence and the quantitative evidence to prove it.
Yes. So I want to talk a little bit. We've talked a little bit about some definitions and the difficulty of definitions, and you're especially known for your work in a subfield called synoptic scale meteorology. What does that mean? And what is the state of that subfield? What was it when you began working in that subfield, and how has it evolved?
Well, synoptic meteorology just refers to the broad weather patterns
Mhm.
on the scale of individual cyclones and anticyclones, highs and low pressure systems you see on the surface weather map,
Mhm.
and the associated upper level disturbances called troughs and ridges, which are areas with calm quiescent weather
So
that
much like what we
go.
would see on the weather news.
Yeah, you might see that on the weather news.
Hmm.
So synoptic meteorology is all about the motions of those larger scale weather systems, which in turn will control where heavy rain might occur, where snow might occur, and where thunderstorms and tornadoes and severe weather might occur within a smaller scale, on the mesoscale, referring to within the larger scale where something might happen.
Hmm.
And then there's the very large scale, the global planetary scale kinds of circulation. You can think of like three sort of levels. Planetary scale circulations might be the broad patterns associated with the El Nino Southern Oscillation
Yes.
events. Um, Synoptic scale phenomena would be broad weather patterns that are associated with, um, say, widespread rainstorms, widespread snowstorms, big heat waves,
Hmm.
cold wave outbreaks on continental scales. And
Hmm.
then mesoscale, referring to the kinds of events when you have a severe weather event, tornado, or a severe hailstorm that might impact, say, the southeastern part of South Carolina, but not the northwestern part of South Carolina because it occurs on a very small regional scale or city scale. And they're all linked to each other. In other words, the very large scale flow patterns control how the synoptic patterns and how the jet streams are going to behave. And then how the jet streams behave are going to control where the mesoscale features will behave.
Uh-huh.
Now, the problem is we're much better at forecasting the large scale flow patterns,
Uh-huh.
maybe a week to 10 days in advance, than we are the synoptic scale patterns, which might be 4, 5, 6, 7 days in advance. than we are the mesoscale patterns, which if we can forecast them 2 to 3 days in advance, we're doing very well. So the
Yes.
bigger the scale of the phenomena, the longer the time horizon you can make a prediction about what's likely to happen. But knowing, for example, that say somewhere in the eastern part of the United States, 8 days from now, since we're going to have a trough and it's springtime, there might be severe weather, but I can't tell you 8 days in advance whether it's going to be in Tennessee, whether it's going to be in northern Florida, whether it's going to be in Virginia, or whatever. We just don't have that kind of skill yet to do that.
And that's why in our own weather forecasts, we often see that the severe weather predictions change, whereas things like the prediction of temperature is generally, we can know about what the temperature is going to be, whether a heat wave or a cold front is coming through much further in advance, right?
Yep, the easiest parameter to predict is maximum temperature, because it's more sensitive to larger scale variation. The next easiest thing to predict is minimum temperature. Minimum temperature is a little harder to predict than maximum temperature because nighttime minimum temperatures, if you live in a valley, it's going to get cooler at night in a low spot than it would be on a high spot. And if there's snow on the ground like now at the time of the year, if it's clear, you get these radiative cooling that say you might have the temperature go down to 0 5 miles from where I'm sitting here in my office, but here at school in the more urban area, maybe 20 degrees. So you have a difference of 20 degrees Fahrenheit between the rural areas where it's snow covered in the little valley and the urban area. But on the afternoon, if the temperature is not going to vary by more than 2 or 3 degrees with the sun out between those same locations. So minimum temperature has a forecast sensitivity on much smaller scales. So that's a little harder to predict. Then when it comes to rain, we are much better at saying, well, whether it's going to rain tomorrow or not than we are how much it's going to rain if it rains.
Yes.
Forecasting precipitation amount is inherently more difficult to do than to forecast whether it will rain or not tomorrow. And my wife's a good barometer of this because years ago she would ask, is it going to rain today? And I would mumble some words and have a coughing fit and give her a forecast. But now she'll ask 3 or 4 days in advance. If it's Monday, she's going to say, is it going to rain on Thursday afternoon or Friday morning? So she's sharpened her question because she accepts that the forecasts have gotten better. I can say something in a longer time range and within a more specific time window about whether or not it's likely to rain than I could 25 or 30 years ago. But I've been trying to teach her. She still wants a deterministic forecast, but the future of forecasting is in the ensemble forecasting and probabilistic forecasting.
It's always going to be a likelihood.
Yeah, right. So your ensemble forecasting is by far the biggest revolution in forecasting that's occurred in the last 10 years. And we're still in the infancy on that. And
what do you mean by ensemble? Is that just taking in?
You have a model forecast, a global forecast model, and you can do 2 things. You can perturb the physics, or you can perturb the initial conditions by a tiny little bit and then run the forecast, all starting from 7 o'clock this morning. And you'll have maybe 25 forecasts of the same thing going out to 10 days. But each forecast will differ because you change the initial conditions of temperature, moisture in the atmosphere, wind in the atmosphere, or you change how you specify the physics of precipitation. So that's called initial condition sensitivity, or as well as physics sensitivity, and you get a divergence of solutions from the forecast model. And so if you have, say, picture an ensemble with 100 members in it, 100 different members. If at a specific point, like Atlanta, Georgia, 60 of those members had a 1/4 inch or more of precipitation and 40 of the members had nothing, then probabilistically, if you wanted to forecast a 1/4 inch of precipitation, you would give a 60%. 60 out of 100 members of the ensemble are forecasting rain. And so you'd have a 60% probability. So that's the future of forecasting and probabilistic estimates. I know a lot of members of the public who say we don't understand probabilities. And I always laugh because the same people who often say that will talk about their horse going off at 5-2 at their local track, and they understand completely what it means to bet money on a probabilistic, a gambler's odds. So my tongue-in-cheek cheap suggestion is to start a weather lottery and put money on it, then the public will pay attention and understand completely what a 30% chance means that something happens.
Actually a great teaching idea for teaching probability.
Yeah.
Hmm. As long as
I
you're not
mean,
using real money.
that's what students really need to be learning today. It's a
Uh-huh.
probabilistic world and just about everything. And
Hmm.
that's the way forecasting is going.
Yeah.
And so probability and statistics are absolutely crucial subjects now, not only in college, but in the high schools as well.
Yes. Hmm. We have another question from the audience. This is from Ken Walter, and he says, in the computer models of weather, what 3D grid dimensions are used? And are there thermodynamic parts to these models? What do you think distinguishes a good model from the others?
Well, a lot of the models are very similar. First of all, it's like a cube. The whole globe is covered. And then you integrate in time steps. Or maybe, for example, like 5-minute time step, you could integrate forward.
Hmm.
But how close the grid points are to one another matters. When you get a bigger computer, if you double your horizontal and vertical resolution, you've increased your requirements by 2 to the third.
Hmm.
So the storage requirements start going up very, very rapidly when you get finer and finer resolution. So it's just like a cube, a lattice, or a matrix that you have, a three-dimensional cube, but it's centered on the entire atmosphere of the Earth. In the early days, when we started doing these numerical models, we just put a wall at the equator and just did the northern hemisphere because the computer capacity wasn't large enough to handle the entire globe. But a wall at the equator meant that the two hemispheres couldn't communicate with one another. We now know how stupid that was, but at the time we did that, we had no choice because
So
the
there was
computer.
no way to take into, for example, into account El Nino or something like that.
That's right.
Hmm.
Yeah, there's a lot of when the Indian monsoon, for example, in the summertime, the warm season monsoon, air from the southern hemisphere flows across the equator and feeds the Indian monsoon, but there was no way to get that into the forecast models
Hmm.
back when because of that. So with these big three-dimensional cubes now and very dense grids, keep increasing the vertical resolution and the horizontal resolution as the computers get faster and bigger in there. So that's how we start representing processes. We're still not at the level where you can represent properly a tropical cyclone, all the processes that occur in a tropical cyclone or a supercell, mesoscale supercell thunderstorm, for example. But we're getting there.
Um, you've also done some work on how land formations and terrain, such as mountains, can affect weather. And so, can you talk a little bit about that work and what you've found over the years? What surprised you?
Well, a lot of people work on terrain features.
Hmm.
The other day, a couple days ago, there was a station in the Oklahoma Panhandle that recorded a high temperature of 98 degrees, Altus, Oklahoma. 98 Fahrenheit on February 10th. That's astounding. Many places up here don't even get to 98 degrees during the hottest summer day. And to have a 98 Fahrenheit maximum on February 10th was just nothing short of extraordinary,
Yeah.
especially considering that the previous monthly record in Altus, Oklahoma for the high temperature in February was 93 degrees. So breaking that record by all-time record for February by 5 degrees was phenomenal. But one of the reasons it was so hot was the air came from the tropical and subtropical Pacific to begin with, and then it was further warmed by downslope flow off the Rockies when it gets into the high plains.
Mm-hmm.
So air literally comes downslope off the Rockies. And so anyone who lives in Denver knows that, as I like to say, wise indeed is the meteorologist who knows which way the wind is blowing when you're in Colorado.
Mm-hmm.
On downslope days, it can get very warm, even in the middle of winter. The Chinook winds, the snow eaters in there, very, very warm. You can get 70-degree days in Denver in January and February on downslope flow. And
So you
a
said
day
snow
later,
eaters?
it's snowing.
What does snow eater mean?
Snow eater means the air is so dry, the snow just sublimates. It's like literally it disappears right before your eyes, not because it's raining. It's like it just sublimates out of its existence.
It vaporizes basically.
It's
Some
a
of the weather.
Chinook. It's a term from the Native Americans from way back,
Huh.
and they used to welcome that because deep snow cover could disappear in 1 or 2 days,
Huh.
and
Interesting.
permit travel, and permit doing stuff, permit
Uh-huh.
harvesting,
Uh-huh.
permit finding food, things like that. So in Colorado, an easterly upslope wind will give you clouds, precipitation, and a westerly downslope wind will give you hot, dry conditions.
Mm-hmm.
So, and then you have these orographic issues like when you have like West Virginia flood in June of 2016.
Mm-hmm.
Very moist air from the west came and entered the Ohio Valley, and they got into the mountains of West Virginia, and there was an old frontal boundary left behind, and you had a concentrated flood um, in that region.
That rainfall, that precipitation just got stuck. Is that what
Well, it's
happened?
just basically very tropical airstream, richly moist, very moist tropical airstream is like a
Mhm.
fire hose. And then where it's forced to ascend in the mountain barrier, you get a lot of heavy rain.
Yeah.
We have these names for them now that people call them these moisture streams that come out of the tropical Pacific, for example, are called atmospheric rivers. That
Mm-hmm.
was the name coined by some people in the late 1990s.
Mm-hmm.
And you see these in the satellite imagery all the time. And where these atmospheric rivers make landfall, you can have flooding rains that are enhanced tremendously by orographic precip, like in California.
And so when it's basically when the warm air that's full of water vapor rises and cools, then it condenses and then it just dumps all the rain
Right.
as it rises to go over the mountain.
Now it can rise and cool over the ocean in a frontal band. Frontal
Mm-hmm.
convergence can force it up. But in addition, when the moist airstream reaches mountains that extend up to 3,000 meters,
Mm-hmm.
then you're going to get a lot of condensation simply because of the forced orographic uplift of the
Mm-hmm.
air, which is what happened in January in California. And right now, in parts of the northern and central Sierras are on track to have their wettest period ever in a non-El Nino year, which I think is hilarious.
So
Um,
that's unusual that for it to be in a not El Nino year and have
yeah,
that
well,
kind
last
of
year was
rainfall
the
that we've
big El
seen in
Nino
California.
year. Yeah, last year was the big El Nino year,
Right.
2015, 2016, and doom and gloom was forecast in California, and they had basically close to normal rainfall. They didn't
Uh-huh.
get, especially in the southern part of California, the heavy rains, the end of the world that forecast that were the end
Yeah.
is near kind of forecasts that were made in the previous fall didn't really verify.
Mm-hmm. Yeah.
I mean,
Because
this
they
year,
had some bad drought earlier, and so it was sort of they were worried about another drought happening that would make everything exacerbate everything. But
but
instead it
right
didn't.
now, it didn't. Right now, in northern and some parts of central California, there's been a tremendous reduction in the drought
Mm-hmm.
from the last 5 years. And in
Yeah.
fact, there are water surpluses, isolated water surpluses starting to show up. And right now, we have a real time potential disaster with the reservoir there.
Right.
Uh,
The potential for the dam to break.
Great.
Yeah.
Yeah.
Mm-hmm. Um, so talk a little bit about about what we've learned about the El Nino and La Nina pattern since you started researching, and it wasn't really something that was part of weather forecasting when your career first took off. Um,
That's right.
but now
El Nino,
it's a huge part
pardon.
of the weather news.
Yeah. El Nino first became a household word in 1982,
Uh-huh.
1983.
Uh-huh.
The public first began to um, notice that. And then again in 1997, 1998. And even when it became a household word in 1982, 1983, we really didn't have the measurement systems in place in the Pacific, tropical Pacific, to really get an idea about what was going on and what was happening.
Mm-hmm.
But as a result of that, a lot of instruments were put in place, which then got lots of great observations for the 1997, 1998. So
And were
much so
those
that
what kind of instruments were used what kind of measurements did they need? Was it more ocean or atmospheric?
both buoy measurements in the ocean, very critical to knowing not just the surface water temperature and how how anomalously warm or cold it was.
Hmm.
But what if you go down 1, 2, 3, 400, 500, 1,000 meters? What were conditions like in the currents and the subsurface water temperatures relative to normal?
Hmm.
Because what was the heat content of the upper, say, kilometer of ocean?
Hmm.
Have high heat content, then cooling wind blowing over the surface is not going to produce a lot of cooling, and the atmosphere will eventually respond to anomalously high heat content in the
Hmm.
ocean, as well as it will respond to anomalously low heat content in the ocean. So we learned about that. Um, and to the point where in 1997, 1998, on the UCLA campus in California, a lot of the outdoor places, there was something called, there was a place called the Bomb Shelter on the UCLA campus, and they had El Nino discount cards. This little little card you put in your wallet. If it
Uh-huh.
rained, you got a 10% discount because it was outdoor place where people ate lunch. Which
Uh-huh.
normally on the UCLA campus you can eat outside any day of the year,
Uh-huh.
but like with only a few exceptions. So they didn't want to lose business. So I have one of these cards, El Nino discount card, in there. It's kind of cute. It tells you to 10% off on days it was raining in
That's
the
clever.
yeah. So it was clever. It was very very clever advertising.
Uh-huh.
One of the things we learned out of that was people thought about El Ninos. Then there was the strong La Nina that followed a year later in
Uh-huh.
1998, 1999. And so the temptation was, based upon such a small sample size, to assume that when you have a major El Nino based upon the extent of the sea surface temperature anomalies in the Pacific, that a major El Nino meant that it was always going to be heavy rain in California all the way to, say, northern Florida and the Atlantic coast, and it would be dry in the northern part of the United States, wet and mild in the southern part of the United States. In other words, the sample size was small, so people made forecasts of basically of a mean of 1 and a standard deviation of 0. And any scientist knows that that's a bad idea.
Uh-huh.
When you have a larger sample size, it's not going to have of events. It's not going to have a mean of 1 and a standard deviation of 0. And that's what we saw last winter. We had a significant El Nino, but it did not produce the anticipated heavy rain in Southern California
Hmm.
that people were forecasting based upon assumption of basically a mean of 1 and a standard deviation of 0. So we had to unlearn some things in order to learn something.
Uh-huh. And so
And
it
so,
seems like as we're getting more and more El Nino and La Nina events under our belts with the kind of technology we have now, we're going to learn a lot more about being able to predict based on those
that's right. But
events.
what we
Yeah.
also know is that there are many flavors of El
Yes.
Nino. Likewise, there are many flavors of La Nina, and they
Hmm.
don't all have the same weather impacts over the
Hmm.
continental United States.
It's also not one of those things that's a switch on and off.
That's right.
Yeah. Hmm. Uh, okay. Let's see. Did I get that question? Yes, that's a question I answered. Okay. So we need to start wrapping up. We're getting towards the end. And I just wanted to talk for a little while about where you think the field of meteorology is headed. I know that's a broad question, but I just like to hear your reflections on uh, what topics would you think are going to yield um, interesting discoveries, and what you would maybe advise an early career meteorologist to focus on right now.
Okay, I think the idea that thinking about the atmosphere as a global continuum is
Hmm.
critical. That what happens here depends on what happens there, where there may be thousands of kilometers away from here.
Hmm.
And that's true anywhere in the world. And so to make predictions for now, next week, or the week after, um, in any location requires knowing the global weather.
Hmm.
And what that means is we need global observations. And there has to be global cooperation in order to get global observations.
Hmm.
Satellites go up and get the observations. So that's an area where there typically, historically, has been a lot of international collaboration on getting the observations, and so on.
It
So
seems like it would be in
thinking,
everybody's interest. Everybody wants to know what weather's coming at them.
Yeah, you
Mhm.
would think it's in everybody's interest, but I've lived long enough to know that people always don't act in their best interest.
Yes.
In fact, they relish doing actions that actually are opposite their best interest, but that's the nature of our species, I guess. Um, so with the computers getting better, the global forecasting will actually be getting better and better. And
Mhm.
so this area, the distinction between weather and climate is going to blur.
Mhm.
Um, there is so much money to be made if you could make a skillful week 2, week 3, or week forecast of temperature and rainfall anomalies.
Mhm.
We're not going to be able to say, at least in the foreseeable future, in my opinion, specific like on 20 days from now, what it's going to be sunny or whether it's going to be rainy as a specific forecast. But we would like to think that fairly soon we might be able to say 20 days ahead of time that the probability is more likely than not that temperatures will be above normal and rainfall will be below normal, even
Mhm.
if we can't say exactly what days it will be hot and what days it will be dry with
Mhm.
any great confidence. But we can say the odds maybe are 60-40 in favor of an extended warm spell or an extended dry spell.
Mhm.
Well, if you're certain businesses really want to know that, just like certain shipping companies might want to know, for example, that it's going to be tropically inactive for the next 3, 4, or 5 weeks. We expect it to be below normal tropical cyclone activity in September.
Mhm.
Well, if you're trying to organize optimum routes for your ships and you know that the Atlantic is going to be quiet, the Pacific is going to be very active for the
Mhm.
next 3 to 5 weeks, that's going to matter
Mhm.
because more and more businesses are global. When you see all
Right.
these acquisitions going on in the business world, these companies are acquiring one another and they're running global businesses. And so they need to have information on the global scale.
Mhm.
So what that means in our educational system is interesting because we need to teach students about global weather patterns and global climatology. Say
Mhm.
you're growing up in Virginia, you can't in Norfolk, you just can't know the weather in Norfolk, Virginia, and think you're going to be able to get a job. I
Yeah.
mean, because what happens in the weather in Norfolk, Virginia, depends on what happens in the Pacific
Mhm.
and elsewhere. And so companies with global operations want people who can think globally but forecast locally.
Mhm.
So that's a huge change.
Yeah.
And being able to interpret numerical model output, a lot of routine weather forecasting is going to become automated. So
Mm.
people who just tweak statistical forecast of high temperature and low temperature and got paid to do that, increasingly in the future, that kind of job is going to be done by computers.
I see.
But what's really needed are people who can oversee what's going on, who really understand and can interpret what
Mhm.
the numerical forecast models are saying, and who can advise a wide variety of clients in the public and private sectors about what to expect and why.
Mhm.
And from a point of view of people being scientists, knowing that everything is so interconnected now and looking at globally, being able to understand all the science behind the global weather connections.
Mhm.
That's really, I think, a very good area for young students to think about going forward.
That's fascinating. We have one last question from the audience. Let me see if I can. Yeah. Okay. So the question is from Diane Timlin, and she says, could you compare what things are like on the job for meteorologists now versus, say, 30 years ago? Even as weather prediction has improved thanks to advances in research and increased computing capabilities, expectations from the public uh, have heightened, and the news cycle has expanded to 24/7. Is the job now more difficult?
I guess it depends whom you talk to.
Mm.
Um, the forecast, we know a lot more, but I would argue that the gap between what we know and what we tell the public is greater than ever, simply
Mhm.
because the Twitter universe does not permit any kind of intelligent conveying of information in 100 and whatever characters
Mhm.
in there. And the 24 news cycle are all about being first, not being accurate.
Yes.
Um, and you have to have nuance when you're making a forecast. There's uncertainty. When you talk about probabilistic information, how do you convey that in a meaningful way? So we
Mhm.
need social scientists to help us out in terms of that's the thing that's more realized now than say compared to 30 years ago. The
Mhm.
art of communicating with people when people's attention span is 30 seconds or less on anything
Uh-huh.
over the course of the day. I mean, how do most people get weather? They look at their cell phone
Mm-hmm.
and they have icons. Well, I mean, that works, but that's basically minimal level information, but it seems to satisfy um, a lot of people.
Yeah.
But there's a real issue. Our TV stations going to continue to pay for meteorologists to deliver the forecast on the evening news. And I look at my young students, how many of them bother, how many of them even own televisions, or how
Mm-hmm.
many of them even own look at regular news anymore. I mean, they
Mm-hmm.
don't do that. So what's going to happen to TV weather news going forward in the next 10 to 20 years? Will that just go the way of a lot of other things, and as people increasingly get their information from what they have in their pockets? I don't know, but it's a sea change in terms of what's going on and how you convey information. So in one sense, it's easier to forecast because you have access to data you didn't have before. You had to do a lot of pencil and paper kind of calculations and analyzing maps by hand in the old days.
Mm-hmm.
Now it's done all by computer, and you can do more. But then there are more demands on your time, and there are more sources of information. There's a towering babble of information out there. And how do you sort out the wheat from the chaff when you try and make a forecast?
Mm-hmm.
So it's both a good news, bad news story.
Yes, and parallels what's going on in a lot of other scientific fields as well.
That's right.
Yeah.
But you have to have the technical skills in any science field today. You have to have the supporting technical skills, being able to program, being able to write code, being able to understand statistics. You need the science, you need the calculus background and the physics background to do meteorology and atmospheric science. And you absolutely need to have the technical skills and the communication skills.
Yes. Yeah.
In the old days, meteorologists tend to be more introverted than that, but that's not going to work today when the ability to communicate with people becomes very important.
Mm-hmm. We have one question. I think we have time for this one last question. This is another question from Ken Walter. He says, "What do you think of forecasting weather as in WHETHER weather? Whether Yucca Mountain, Nevada, the weather there at Yucca Mountain, Nevada, will remain dry after 10,000 years?"
Who knows? Um, that's a forecast. You can get anything you want out of that, but will we have continental
Too
drift
far
in
in the
10,000
future.
years? Yeah, way too far, way too far in the future. All that I can say in the short run is getting noticeably warmer, and if you're not noticing that it's getting warmer now, and because of human activity, you're just not paying attention.
Yeah. Well, thank you so much, Lance, and good luck with your research. And thanks for taking the time to talk to us.
Thank you for the opportunity to do so.
Mm-hmm.
Best of luck to everybody.
Thank you. Bye-bye.